In this video we're going to look at decibels. Now, I come from a IC design background, and the types of chips I was designing were really for TV receivers. So depending on which industry you're in, some of this might not apply and some of it might be slightly different, but let me work through some of the basics that are absolutely the same for all industries. So when we started off, before we had calculators, multiplication and division were difficult, time-consuming processes. So we needed to have another process in order to multiply and divide. So enter the idea of the logarithm. So the idea behind this is that if you were going to multiply two numbers, say 8 times 4, which equals 32, you could write 8 as a power. So you could write that as a 2 to the power of 3. You could write 4 as 2 to the power of 2. You could then multiply these together. So if you multiply 2 to 3 times 2 to the 2, you would get 2 to the 3 plus 2. Okay, so when you multiply together, you add the indices. So therefore, that's the real direction we're going. Multiplication becomes addition. So that's equivalent to 2 to the 5, which equals 32. Okay, which is the same as 8 times 4. So it's all held within that simple line there, the idea of the logarithm, and multiplication become addition and the division would become subtraction, because whenever you're going to divide powers, you will subtract off, divide numbers, you would subtract off the powers. So it means that we can use powers to multiply and divide. So what we'd have done previously, before we had the calculator, we would have tables of logarithmic tables and inverse log tables, or a slide rule in order to work out the multiplications. Now, I'm a bit younger, I never had to use these, so you're talking about maybe in the all the way through to maybe the early 70s, people were possibly using these log tables. So if you were to write down the number in terms of your indices, so first of all you get a table of indices for every number for a particular base. In this case here the base is 2, so we convert to your indices, and then once you've converted your two numbers to indices, you could then add the indices together, and then you could go back to another table of anti-logs and find the inverse of that log in order to give you the final answer of 32. Okay, so that's the three things that would have to be done. So 1 and 2 would be done by tables, and 1 and 3 would be done by tables, and number 2 would be just an addition. So here's an example there. Okay, so if you had in decimal numbers 0, 1, 2, 3, 4 all the way up to 32, and then the base 2, well, we'd be looking at that and saying the value 4, you'd have to raise 2 to the power of 2 to get 4, you'd have to raise 2 to the power of 3 to get 8, you'd have to raise 2 to the power of 5 to get 32, so on and so forth. So in order to do this multiplication, 4 times 8, you would come along to this table here, which would be a table of your logarithms, and you would be base 2, and you would go down to the table and you would find the number 4, you'd go along to the table and you would get a 2, so you would take a note of that 2. You do the same for 8, you would find the decimal 8 in your log table, find the value of 3, you would then add the 2 plus 3 to get 5, so that's number 2 above, so you're doing the addition here, and finally the third part of it would be the conversion. So you'll be going to an anti-log table and converting from your logarithms back to the decimal, which will give you a number 32. Okay, so that's a very simple example, but if you had really large numbers with, say, or fractions, then it would be quicker than trying to work it out by hand. Okay, so that's the basic idea. Now, if we were to draw out the actual function here, so we have a y and an x, and we'd have a function y is equal to, it's actually 2 to the power of x. Okay, so y is equal to 2 to the power of x, so that's the function there, 2 to the power of x. Now, note here as well that we don't need to use the base 2. Okay, we could use any base we say any base greater than 0. We can't use a negative base, because if I was to use a negative base, then I would have possibly say -2 to a particular power. Now if it was -2 to the power of -1, then it would be root of -2, which would give us a complex number. So we don't want any complex numbers in it, so we always make sure that the base is greater than 0. So I've drawn a few in here. So there's 2 to the power x in yellow there, and there's 10 to the power x, and you could also use it in fractional terms. There's a half to the power of x there, and there's half to the 1 upon 10 to the power of x there. Okay, so you can see these drawn out. These are the actual functions. Now all we're really interested here for what we're doing, or in terms of electrical engineering, is to the base 10. Okay, so we're interested in y equals 10 to the x. So what is the actual logarithmic function? What does it look like? Well, we need a function that converts back from the logarithmic form to the decimal form. So this is really step 3 we've seen in the last page. So that's an inverse function. So if we had a function there, say y equals 10 to the x, in order to get the inverse, what we do is we reflect it in the line y equals x. Okay, you can see that there, because if an inverse function, if a function takes x to y, an inverse function will take y to x. Okay, so in order to get the inverse function, we just swap over our y's and our x's, and we do that by mapping through this line y equals x. So that's an inverse function of this y equals 10 to x. That's a logarithmic function. So what we do is we say that the x is equal to log to the base 10 of y. So we say y equals 10 to the x, then we could say, for example, 100 equals 10 squared. Then the inverse function there, the logarithmic function, would be 2 equals log to the base 10 of 100. So really what we're saying is, what number do we have to raise 10 by in order to get 100? And the answer is 2. Okay, and we put 2 would be up along this instant here, be up along the y-axis here for this inverse function. Okay, so a wee bit of maths there, but we'll go on to some more kind of practical stuff here. So the idea of the bell was introduced in the early 1920s at Bell Labs in order to facilitate the experiments they're doing on power efficiency of telegraph lines. Okay, so they're doing experiments where they're putting a particular signal or power into a line, and then they're seeing how much the signal gets degraded along the length of the line, so how much power they get at the output. Okay, so they're looking at the input power and the output power, so they're looking at the losses along the line. So rather than have the losses along the line in the terms of power out upon power in, which is just a number, they do it in terms of a logarithmic scale. Okay, and it was named the Bell after Alexander Graham Bell, seemingly. Okay, so that's the next equation here. The Bell is defined as log to the base 10 of the power ratio of power out upon power in. Okay, so that's power gain, so or loss. So if it was a positive number, it would be a gain. If it was a negative number, it would be a loss of a circuit in a logarithmic scale. So an example here, we have a little gain times 2, so that's times 2 in terms of power, so the power gains times 2, so we're putting in 1 watt, we get 2 watts out. So we can say that the gain is equal to power out upon power in, which is 2 upon 1, which is 2. But in a logarithmic scale, we're saying log to the base 10 of 2, which is equal to 0.3. Okay, so I suggest you get your calculator and go and find, actually put the numbers in so you know where these values are in your calculator. But we seldom use the Bell. Okay, it was superseded, and we're using another factor of 10, so we call it the decibel, which is the same as a bell but multiplied by a factor of 10. Now I suppose we could go online and check and see why they used that, but I think that what I previously had been told, it just made the numbers a little bit better that they were using. So instead of using a gain of 2 is 0.3, the gain of 2 becomes a value of 3. Okay, so But you could have a wee look up in a wiki somewhere to check out the history behind that. Okay, there's plenty there for it. So the decibel then is going to be 10 log to the base 10 of P out upon P in. So in that previous example there, it means that the decibel is going to be written as the power out and power out, and it's going to be 2, so it's going to be 10 log to the base 10 of 2, which equals 3 dB. So a gain of 2 in terms of a power is equal to a 3 dB gain. Okay, so the next equation then we can write down is power gain in dB is equal to 10 log to the base 10 of power out upon power in. Okay, so there really is only one equation when it comes to gain, okay, and that there is this equation here. Okay, we'll also see it written in terms of a voltage, okay, but in terms of voltage, okay, that's going to be another way of looking at this fundamental idea here of a power gain. Okay, so remember as well that the gain in dB, it's just a ratio, okay, of two numbers. It doesn't have a unit, okay, so it's like it's a gain as in times 2 or times 5 or times 20. There's no unit involved in it, okay, it's not watts or volts or amps, it's just a number. Okay, so let's head on. So mentioned there that we can also look at the gain in terms of a voltage gain, but before we do that, we're going to look at an idea of a maximum power transfer, okay, because it's all kind of related. So if we had some gain element here, okay, so that's a little triangle, so that's some amplifier, and we had some source here, then the amplifier is going to have a resistance associated with it. So that's the load resistance, that's the resistance looking in the terminals of the amplifier, and also your load is going to have some resistance associated with it as well. Okay, so your source is going to have some resistance associated with it. So this is the source resistance and a load resistance. Now, not necessarily in all types of engineering, but certainly in a lot of them, certainly in television receivers, for example, and most IC design, what we're interested in is maximum power transfer. Okay, so what we're going to do is we're going to make sure, in order to get maximum power transfer, what we have to do is we have to make the load resistance is going to be equal to the source resistance, and you can see that here, because if you say that the current through this little network here is the voltage Vn divided by the total resistance, which is Rs plus RL, but we know that the power is equal to, or the power of the output here is going to be equal to I squared times RL. Okay, so it means that we can then say that power is going to equal, well, the I is going to be this thing here, so we take that and we square it, multiply it by RL. Now the question is, when is this going to be maximized? Okay, so at what point, when we vary RL, the load resistance, at which point will the power be maximized? So it's a little differential problem. So we're saying that they want it to be a maximum. Okay, so it's going to be either a maximum or a minimum whenever there's a stationary point. Okay, so whenever you've got a graph like that or like that, okay, you're going to have either a maximum or a minimum. So we'll find out when the rate of change of the power with respect to the load resistance is equal to 0. Okay, so what we want to do is take this here, we want to differentiate it. Okay, so we're differentiating this thing here with respect to RL. Now, this is not a course in calculus. I do have a course in calculus of variations if you're interested in it, also on Udemy, but this is really an op amp, and it's meant to be some form reasonably practical, so we're not necessarily want to go into massive detail, but if I was to differentiate that there, I would get this equation here. Now if you're insisting on differentiating it, then it's reasonably straightforward, because we're differentiating with respect to RL, so it means that RS and Vn can be treated as constant, so that's just the same as like writing say 5 upon 5 plus x all squared times x. So if you differentiate that with respect to x, you need to use the product rule for differentiation. So you have two forms of differentiation, and the chain rule as well, because there's a square term here. So I have worked through it, but I just don't want to write the whole thing out because it just gets a bit cumbersome. So we were to differentiate that there and make it equal to 0, so then we can say then that from above here, if you note that the Rn plus RL minus 2RL would equal 0, it would ensure that RL would equal Rn. Okay, so let's do a little bit of maths there. There are other ways of deriving that as well, other than using that differentiation. It's just the one I prefer. So when we design circuits, we usually refer to the input resistance, and the designers of, say, integrated circuits will design them, and they'll say that in order to for you to interface with them, they'll tell you what the input resistance is. Okay, so in most instances it will be 50 ohms or 75 ohms. Now it might be up as well, I've seen 125 ohms used as well, but generally these will be the two input resistances that they're going to use. So now we can get back to the voltage gain. Okay, so voltage gain in terms of dBs. So we've seen that the power gain is defined as 10 log to the base 10 of P out upon P in, but we know that the power is directly proportional to the voltage squared, so power is going to be voltage squared upon R. Okay, so it means that we could write that voltage gain, as 10 log to the base 10 of, well, the power in terms of the voltage is going to be the V out squared upon RL divided by V in squared upon our RS. Now this is the thing about the maximum power transfer that we just worked out. In order to get the maximum power transfer, we have to say that the RL would have to equal RS. Now that's the reason for manufacturers of these chips telling us the input resistance, okay, being 50 or 75. That means that we can produce our source into the system and making sure that that source is either 50 or 75, so it matches. Okay, so it means then that we can rewrite this here, and just through a little bit of logarithms, if you've got the square of a value in a logarithm, you can take the actual value of the square out and multiplying it. Okay, so that's just a little bit of maths. You can check that up in any maths book. So that then becomes 20 log to the base 10 of V out upon V in. Okay, so that there is the voltage gain in dBs. Okay, so it means that the voltage gain in dBs is going to be twice as much as the voltage, the power gain in dBs. Okay, so a gain of times 2 in terms of a power ratio would be, say, 3 dBs, but a gain of times 2 in terms of a voltage ratio would be 6 dBs. Okay, so a little example there. So if we've got a 1 volt in, we've got a 2 volt out, and our gain is times 2, so in terms of voltage it's times 2, so we can say then that the voltage gain is going to be equal to log to the base 10 of 2 upon 1 times 20, which is 6 dBs, but the same value in terms of a power would be 3 dBs. Okay, so in terms of the voltage here, if we had a times 10, and you can put the values into a calculator and check them out, plus I've also got a table here that's accessible. You can download it with all of the values written in tabular forms, but a times 10 would be a 20 dB gain, times 100 would be 40, times 1000 would be 60, and so on and so forth. Okay, so times 10,000 would then be 80. Now we'll move on now. So what we want to be able to do whenever we're designing circuits is we want to be able to not only work out the gain of amplifiers, so that's an amplifier there, so we want to work out the gain in terms of a power gain and also a voltage gain, but we want to be able to take an input signal into a little amplifier, but we want the input signal to be actually in terms of dBs as well, so that we can take our input signal in dBs and then we can work our way through, say, a design which might have a low noise amplifier, an automatic gain control, some IF filtering, for example, and we want to be able to just add the input value in dBs onto the gain in dBs as well, so that we're not doing any multiplication or division. Everything's just done as simple additions. But in order to do that, we need to be able to define a value of we need to be able to define a voltage, or say a current, in terms of dBs. Okay, so what we do here is we want to, an example there as I've shown, we want to take our amplifier and have a voltage here which is in the same units as the gain, so we can add one on to the other, or the same units as the power, we can add one on to the other. Okay, so we do that by expressing the dBs with respect to an absolute value. So we can do this in two ways. We can express it in terms of an absolute value above a particular power, and we could do it using an absolute value above a particular voltage. So we'll look at it in terms of a power first of all. So we can write it out, and you'll have seen it written out as dBW, or dB milli W, or dB micro W, and sometimes you won't even have the W there associated with it, because it'll be understood from the work that you're doing that you're actually working it in terms of power as opposed to voltage. But obviously for explanation I have to put the W there in front of it. So dBW really says power, it's in dBs above 1 watt, or the power in dBs above 1 milliwatt, or the power in dBs above 1 microwatt. So we can work out the value of, let's say for example, dBW. So dBW is going to be 10 log to the base 10. Now it's a power ratio, a power divided by another power. Okay, so it's 10 dB milliwatts, so it's 10 dBs, it's dBs above a milliwatt. So 1 times 10 to the minus 3 is a milliwatt. Okay, so that's that's the reference power, and the other power here is in terms of an RMS value for your voltage signal, and it must be as an RMS value. Okay, it won't work if you don't do it as an RMS value, and the reason to put it in as an RMS value because that is the equivalent DC power. Okay, so you take your peak signal, divide it by √2, that gives your RMS. Of course it's got to be squared, and the resistance here is the 50 ohm system, so it's divided by 50, and you're taking the 10 log of that. So that there is another equation there, equation number 3, and allows us to work out our power in terms of our, allows us to work out an absolute value of a power, okay, into a 50 ohm load. So say for example you had 0 dBm, 0 dB milliwatts into a 50 ohm system. Well, we're really saying it's 0 dBs above 1 milliwatt. Okay, so 0 dBs is really just times 1, so it is just 1 milliwatt. Or a 10 dB milliwatts into 50 ohm would be 10 dBs above 1 milliwatt. Okay, so it would be 10 dBs above, 10 dBs above is actually times 10, which is 10 milliwatts. And 20 dB milliwatts into a 50 ohm would be, well, 20 dBs above 1 milliwatt, 20 dBs is times 100, so it'll be 100 milliwatts, and so on and so forth. So here's a little example here. We've got our amplifier, the input impedance of the amplifier, resistance amplifier is 50 ohms. So we match that with a 50 ohm source. let's say we're putting in 100 millivolts peak, and let's say we get 200 millivolts peak out of it, then we could look at it, we could say that the power in dB milliwatts into that 50 ohm system is going to be equal to 10 log to the base 10 over, well, it's 100 times 10 to the minus 3 upon root 2, so that's the RMS. And if we square that divided by 50, it will give us the actual power. Okay, in this instance here, it gives us a power of 0.1 milliwatts actually, if you were to multiply that out. So whenever you divide that out and take the log of it, you get minus 10 dB milliwatts. So that's really saying that the power here is going to be equal to 10 dBs minus, which means below, so 10 dBs below 1 milliwatt, okay, which is going to be 0.1 milliwatt. So we're putting 0.1 milliwatt into this system. Now, let's say we know that we're putting in 100 millivolts and get 200 millivolts out, so the gain in voltage terms is going to be times 2, okay, which is going to be, in terms of power, is going to be a double it, which is going to be times 4, okay, the power gain. And you know that the power gain is going to be double it in terms of the voltage gain, because we've seen that the voltage gain is going to be given by the 20 log, okay. So let's have a look. So it means then that the output power is going to be the input power plus the gain. So the input power, an actual value in terms of watts, is going to be minus 10, and the gain is going to be plus 6, so it's going to give us a minus 4 dB watts. Okay. So we could also write the absolute power in terms of, in terms of a power, we could write it in terms of a voltage. In terms of voltage, it's going to be 20 log to the base 10 over peak divided by root 2, so that's our RMS voltage, divided by, in this case it's microvolts, so it's 1 times 10 to the minus 6. Now this has the added advantage that it's impedance, the input resistance independent. Okay, there's no resistance in this term here. So 100 dB microvolts into a 50 ohm load is equal to 100 dB microvolts into a 75 ohm load. So almost finished here now, and we can have a wee talk about this once we've finished it and the usefulness of it all. So the conversion between a 50 ohm and a 75 ohm system, so if we had a dB milliwatts into 50 ohms, is going to be given by this equation. dB milliwatts into a 75 ohm is going to be given by this equation. So if we divide both out, we get a value of minus 1.76. So it means that in order to convert, if we were in, say, dB milliwatts in a 50 ohm system, that's going to be equal to a dB milliwatts into the 75 ohm minus 1.76. Okay, so there's a difference of 1.76 between the 50 and the 75 ohm systems. Okay, now there are a few other things that we can add into this about conversions between dB microvolts and dB millivolts, and there's a few other extra things that we can add in about maybe steady dBs. We sometimes say dBc, that's dBs above a fixed carrier level, a fixed signal. So we can go on and on and on with this. I worked for 7 years as an IC designer in analog RF, and we dealt with these things day in, day out. Found it very useful whenever you were in a lab with a chip, and you had the chip on say a spectrum analyzer, and you were checking the output signals. I found that using dBs was very useful. Sometimes usually in a daily process, whenever you're conversing with other engineers, you're talking in terms of logarithmic scales. But for me, after years and years of it, I did realise that every single time you were working on your systems, before you did anything, or really to double check, or really to make a sanity check and everything, you just converted everything back to real terms, meaning real voltages, and just checked through with real voltages, which really made the the usefulness of the logarithmic scale a little bit redundant. I do believe that if we'd gone back and we had calculators in the early 1920s or the late 1800s, we most probably wouldn't have invented the dB scale, and none of it would have, we wouldn't be using any of it, and it would just be real values that we'd be using. So in effect, if you've got a calculator, you don't really need any of it. But that's just my opinion, and possibly other people from other industries might have a slightly different opinion than that. Another thing I've found as well is that it does tend to be overused where there's absolutely no need for it to be used, and sometimes, how to put this politely, sometimes people with not a great amount of maybe mathematical knowledge like to use it because it gives themselves a little bit of kudos, and it sets them apart from the average Joe a little bit, so it might make them appear to as if they know a lot more than they actually do. You know, I have seen that quite a few times. So anyway, that's all there is for this video, and I'll get you on the next video. Okay, goodbye.